tell me when to start.
Oh, let's start.
Okay, let's start. He will come in to get the picture pretty well. So, I think we all know this story. Actually, somebody told me yesterday, we know Schrodinger's cat is definitely dead. Cats don't live for 80 years. So he's right. Schrodinger invented this story to show the absurdity of some of the interpretations of quantum mechanics that were happening in the 30s, which had to do with, the story was, so you have a radioactive element in this box that has let's say a 50% chance of having decayed, giving out an alpha particle in a certain time, let's say 15 minutes. It's a neutron, for example. If it does, then it triggers a Geiger counter, then flips the switch, and it smashes a file, a poison, cyanide, which would kill the cat. But because reality is to do with observers and measurements, and even consciousness in some case, until somebody opens the box and look inside to see if the cat is alive or dead, it's in the superposition of states. In other words, the wave function evolves all the way to have the wave function of a cat in superposition with an alive and dead state, which perhaps we all agree is nonsense. I don't know. I think it's nonsense because, and I will explain why I think it is. So those stories have to do with observer. Observer, usually a conscious observer, like us, or to do with measurement, quantum measurement problem. But what are these? They don't seem to be very well defined. In fact, they're not well defined. And we now know that the universe started with a Big Bang about 30.7 billion years ago in a very simple state and evolved with gas and stars evolving. And I think it's a reasonable assumption that at least for the first hundreds of millions of years, when there was no time for complexity to evolve, no time for carbon. Carbon wasn't part of the Big Bang, it came from stellar explosions after being cooked in stars. No conscious life, right? So I think we can all say it's reasonable that there's no conscious life at the beginning of the universe. And did the universe evolve into one sort of a wave function with 10 to the 80 dimensions all that time until a conscious observer appeared? But what's a conscious observer? Not defined. In fact, none of these things are yes, no. I mean, so here, for example, I mean, I put this in because it's a nice picture of life on Earth, right? And are these thinking? Are they conscious? It's pretty clear to me that they all are in some sense, but I don't think that either thinking or consciousness is a one-dimensional thing. You either got it or you haven't, or you can measure it with one number. I imagine that these creatures observe, but they evolved from single-celled amoeba. So somewhere along that chain, is there anywhere along that chain when you could say that up to that point there was not consciousness, and beyond that point there was? And that seems pretty unlikely, a ridiculous idea, because consciousness must have evolved from some to where we are now at some state. So also the idea that because I am conscious and I open the box, but if I was unconscious the box was open, that's going to make a difference to the state. That's a very beyond the standard model thing. That means beyond standard model, that means some physics beyond any physics we know is actually having a physical effect, like telekinesis or something like that. So, so let's now. So these things are indefinable, non-linear.
All about consciousness, right?
Well, observer. Measurement as well. Observer and measurement. One can define measurement, but one doesn't say just the measurement. You have to be clear about how you define it, and I'm going to try and be clear about how I define it. Okay. So, and no magic moment. No magic moment when consciousness suddenly, or observers observers were suddenly able to collapse the universe's wave function, so-called instantaneously, as if anything can be instantaneous in special relativity, right? It depends on your frame of motion and what's instantaneous and what's not. So, I believe absolutely in special relativity. I'm not going to say anything against that, I think, in my argument. So, if you would say that an observer or a measurement collapses this wave function instantaneously, that could only be in one frame of reference, okay? And another frame of reference, something happening somewhere and elsewhere would be at different times. So actually, that does bring into the question of frame dependence of simultaneity, which is all part of special relativity, and whether you can have things propagating in space-like as well as time-like directions. Okay, so here's the usual sort of space-time diagram where time is this way, one-dimensional space is this way, called x. Okay, and this is the speed of light, so c for 1. And anything happening here, which is normal matter particles, that is called time-like motion. And over here is space-like. And you know, space-like, if particles would move in a space-like manner, they would be like tachyonic, they're traveling fast at the speed of light. Now, actually, such motion is allowed on a small scale, and we see it every day when we, for example, collide two protons together, and they scatter off elastically. Okay. Now, well, I've drawn it that way, but I could more like usual way we draw it like that. Proton. Now there is momentum exchange between these protons. The protons come out with exactly the same energy they came in with, but they've changed momentum. So I won't talk about what this exchange thing is, but there's full momentum exchange between them, and in the central mass frame, there's no energy transferred, only momentum. And you know that the speed of a particle, call it beta c is the momentum over the speed, momentum over the energy, sorry. So when you have momentum exchange but no energy, then beta c is infinite, and that is going in this direction. But it only happens over a tiny distance, and you're allowed to, say, exceed this light barrier over small distances because of the uncertainty principle of Heisenberg, which allows energy to fluctuate and momentum to fluctuate as long as you do it within a small distance. Anyway, that's a bit of a diversion, but coming into how space-like a wave function collapse, if you have a wave function spread out in space, and at some time it appears as an electron at some point in space-time, and the wave function then is no longer, that's called a collapse of the wave function, and that happens in a space-like manner. But I'll come back to that. So now I want to introduce actually an example of what I'm talking about, which is really so instead of taking in a radioactive source, I'm taking a neutron because neutron's simple. Let's take a single neutron. A single neutron. Imagine I made it. I've got it in a vacuum vessel, sitting in there, excluded magnetic fields. There's only one state for the neutron. It's there. If it was in a magnetic field, there are two states, up and down, but pointing with and against the field. Just one state. Now, then it decays at some random time, but with a lifetime of about 13 minutes, 14, maybe 15 minutes, to a proton, electron, neutrino. So the randomness is built in and tested. That's part of quantum mechanics. I'm not going to talk about that. But what I'm going to talk about is entropy, in particular microscopic entropy, because entropy comes from thermodynamics and so on, and it's about ordering of systems. But we can define microscopic energy, which is not directly to do with heat, as the number of possible microscopic states consistent with the macroscopic state. What means that this neutron sitting in there in a large vessel, and after it's decayed, I've got proton, electron, neutrino. This was a single state, so its entropy was 0, the logarithm of the number of states. Number state 1, log W, log 1 is 0. But afterwards, there's a huge number of possible states of the final state. The proton, electron, neutrino, there is a countable number of states depending on phase space elements, okay? So, and it's big because the three-body decay, and so you can have, you know, put in there some sort of Dallas plot of the things, but you can count phase space elements. Well, first you have to observe about energy momentum conservation, so that restricts you. I mean, you could say, well, there's 3 momenta here, here, and here, and that's nine components. So 9-dimensional phase space, but you've got 4 energy momentum conservation, comes down to 5-dimensional phase space, and then it's rotationally invariant. So anyway, you still have a large dimensional phase space, and the elements in that phase space, which can be taken to be like given by Planck's constant, is a large number. So the entropy jumps. The entropy jumps when the neutron decays. And my argument is that it is that we should replace measurement with what we call entropy jump. Okay. So you can say, well, I'm just using a different word for measurement, but let's forget about observers, consciousness, rules and scales and things like that, and just say entropy jump and see where that leads us. So then I suppose that now the amplitude for this decay is time reversal invariant, as far as we know. In other words, the reverse reaction can happen with the same amplitude. However, it's extremely unlikely to get a proton, electron, and neutrino all coming together at a point with exactly the right mass to make a neutron. Extremely unlikely, except in one circumstance, which is if the universe was to come back down to a big crunch at the end, and all matter is forced to an extremely small place, then the reverse reaction will be happening all the time. And when you have, say, an electron emitting a photon, going past a nucleus emitting a photon, and then emitting another photon, this is increasing entropy because what was a simple state before goes to a photon plus an electron, so on, and nucleus would recoil, whatever. So every interaction is an entropy increase. Even elastic scattering is, because there are many possible ways the final state, directions the final state could go in. But this is a clear example, I think. So what I suppose happens is that that the protons and neutrons and electrons, as they emerge, and it's interesting to think about the time scale of this decay. I mean, the decay is extremely long-lived. Neutrons 15 minutes long because it goes through in a virtual W, and the W is a very heavy particle, right? So, but these then, I suppose, proceed as waves. So there's a psi. You know, so here's the neutron, and here's the proton, electron, neutrino, and I imagine these as propagating as waves. Okay, it's not for space and time, and they do that until the next entropy jump occurs, the next S jump, entropy jump, which occurs when you hit the walls of the vacuum chamber, for example, and the electron then can, or the proton can ionize an atom, and every ionization event is an entropy jump because you started with, you started with your atom, and then you kick an electron out, and there's a lot of many possible final state configurations of the ionized atom. Therefore, every ionization event is an entropy jump. So I imagine that the proton, electron, and neutrino waves propagate until an entropy, until one interacts. It's not likely to be a neutrino, but and that then, I say, it collapses the wave function at that time. And now, if this is in a vessel, and let's suppose that the speeds of the electron and proton are the same. So in one frame of reference, it could be the electron interacting first, and in another boosted frame, it could be the proton. But that has to not matter because it's got to be frame independent. So but it does mean that the wave function of the electron is affected by the wave function of the proton when it happens. But I'm not using the word instantaneous because it's got to be frame dependent state. So here, every interaction, ionization, etc., is an entropy jump and a wave function collapse. And notice one thing, that entropy is not defined at a point in space or point in space-time. It's defined on a system. And in this case, the system is the proton, electron, and neutrino. And the wave function collapse is also it's not a local thing. It's non-local. They're both non-local things. So let's see where I go from here. So here's no, okay. So here's what we all experimental physicists we all see this is our bubble chamber picture, a Fermi bubble chamber, and you've got all these beautiful this interaction, the neutrino nucleus collision. You've got all these beautiful curly tracks in magnetic fields. You zoom in and you see strings of bubbles above it, right? Or a drift chamber. This is that's the next picture, but it's the same.
What does the scale make on the left lower corner?
Right. So
bubble. What does the bubble say?
These are about 100 microns across.
100 microns.
But the bubble itself is not one interaction. It's a product. An electron, for example, comes through the liquid, and first it happens to ionize one atom. Okay, to kick the electron out of the atom, and then that recoiling electron and the recoiling atom has got some energy. It's taken a bit of energy from the electron, and that just heats up the bubble of the liquid. Now that is another entropy generating thing because the heat is also, and then you expand the thing and you create the bubbles, and so already between the ionization of the one atom in the liquid and the formation of a bubble, you've gone through a whole cascade of entropy increasing steps.
Interesting that all the bubbles are about the same.
Yeah, well, okay,
standard bubbles.
Standard bubbles. Of course, you collapse them. I think they're somewhat different size.
A little bit different.
So Albert's just come in. So what I've been arguing is that measurement and conscious observers and so on, all indefinable, non-linear. There was no magic moment in the universe when suddenly these appeared and they weren't there before. So what I am doing is proposing that measurement really means a jump in entropy, which has a microscopic entropy, which is the logarithm of the number of final states available to the system. So every ionization event is a jump in entropy, and it doesn't go, the probability of going backward, it becomes infinitesimal when the jump is big. So, and that is when I would say, in the language, the wave function collapses. So the particle coming along this path, as it goes along, it's ionizing an atom or molecule in a liquid. That is in itself is an entropy jump because there's many possible final states of the atom, and then it's amplified and then turned into a bubble by the expansion. And each time that an event like that has happened, then you go back to the wave function description. So if I can just think of it as we draw it as lines, right? Electron, ion, atom, and electron. But really, coming in, when it's not interacting with anything, you have to consider it as the wave function psi of x and t. It's a continuous function. It's deterministic. It evolves deterministically. Nothing random about it. Like in young slits, it goes through both slits. This psi goes deterministic. You calculate that. But when it ionizes or interacts in any way with anything, it has to, I think has to cause, the interaction has to cause an increase in entropy. And that is when the particle then is here. It's found to be here. We can then observe it by looking at the bubble way after the event occurred. It's not collapsing when we look at the picture. But then the electron or whatever goes off as another wave increasing deterministically, but whenever it interacts, of course, you have to have energy momentum conservation. So it can't be over here. You know, but of course, the energy momentum conservation it doesn't have to happen on a microscopic scale because of Heisenberg uncertainties, but on a bigger scale it does. So that's where I'm going with this. And then so that so-called collapse is non-deterministic. It's probabilistic. So as we know, the probability of finding, when I say finding the electron at a point, I don't mean finding the electron at a point, I mean the electron interacting at a point. Because, you know, when you talk about young slits or something, you say, well, you know, the electron wave psi goes through the two slits deterministically, and then the electron appears at a point on the screen. The electron doesn't appear at a point on the screen. At some point on the screen, there's an interaction between the electron and the screen that jumps in entropy, and that then collapses the wave function. And it has to happen in a space-like fashion, but so I don't want to say instantaneous because I don't simultaneity is not relativistic invariant. Okay. So now we have if we go back then to this, so you know, so this is nonsense because as soon as the radioactive atom in there decayed, entropy jumped, no going back, that's it. So the cat's determined to be dead or alive when that interaction happens, and nothing to do with anybody looking in the box or not, or observers or measurements. So that's that. So and here's another picture with, okay, so this is actually UA1 bubble chamber. No, sorry, UA1's drift chamber. There's a very nice pictorial drift chamber, at least in one view. The orthogonal view is a horrible mess because of charge division, but here's actually an electron coming out straight from a W decay, which is why the picture is sort of famous. And you see here these ionization events. Of course, what you're seeing is not the initial ionization event, but what happened when you had a whole cascade of ionizations from the electron getting near the wire where the field is big, and then you get an avalanche occurring. So ionized atom to avalanche to amplification, the signal to recording, each one of those is symbolic of a jump in entropy and therefore a wave function collapse. So the wave function of this electron coming out of here is evolving between ionization events deterministically, but as soon as it ionizes an atom, or in any way, I mean, it could even just excite the atom, doesn't have to ionize it, but that is going from a simple initial state to a state that has many possible, you know, energy momentum conserving final states, which is where you get this large entropy. So that's the sort of picture here, cascade. It's a gas in the drift chamber. And I mean, I don't think, you know, this is a philosophy meeting, but I don't think any active experimental physicist would consider that these events in the CDF or you know, CMS things are only real when somebody looks at the event, because in fact we don't even look at the events. Usually we plot them in histograms and stuff like that. They really happened there. So this is saying the same sort of thing. Same thing, every stage in here, entropy jumps, and of course it has to obey all conservation laws, but when you are looking in actual very small regions of space, like the neutron, then, well, as we know that, you know, energy momentum conservation can be violated according to Heisenberg, so a neutron coming along here is a down, and up, and then it goes to a down, up, and up by emitting a W, okay, and that goes to electron neutrino, and the W mass is so high that of course this can't happen really, but you can violate energy conservation for the tiny amount of time which allows this to happen. So that's, where am I going down with this? So, also, I mean, even it doesn't have to be an ionization event. Cherenkov, take a Cherenkov counter. So their particle goes through a medium, and it influences the atoms, which then radiate photons. So that the radiation of Cherenkov light is another non-ionizing example of interaction of that, where the particle as it goes through is it seems to be moving deterministically, but only because the collapses are happening very often all the time as the photons are emitted like that. So, so here's a famous sort of now Atlas and CMS plot, the mass of 2 photons, cross section, you see the thing, which is an excess over a continuum. You've seen the Higgs boson, of course. You've seen a bump in a plot, but when those events happened, who knows? I mean, a year ago, 6 months ago, but we still see this as evidence. But this so maybe so a lot of I've tried to talk about wave function collapse to some theorists, and a lot of them say, don't talk to me about wave function. Shut up and calculate. Calculate Feynman diagrams without talking about it, and you can calculate G minus 2 and so on. And Feynman said no one really understands quantum mechanics. I don't claim to understand quantum mechanics. My only claim really is that we should not talk about observers, consciousness, measurements at all, and we have to accept that wave function collapse, which is real somehow, is space-like, can be space-like without violating special relativity. And special relativity, I think, prohibits any particles with mass, with real mass, from traveling faster than the speed of light. But that's not to say that we collapse a wave function, which doesn't have mass. Its potential mass is in there, but it doesn't have mass that can collapse like that. So, I say again, the wave function should evolve in accordance with deterministic dynamical laws. It's spread out from source, be non-local, but at any point in space and time, the probability is given by the complex conjugate times the wave function, and that gives you the probability. So that's all fine. So what is new is really, I think, well, new at least. I'm arguing that it's the entropy, it's the question of entropy, that microscopic entropy, which is S times the logarithm of -6. So this is the usual magic about young slits, where you can build up a pattern of interference when you only have 1 photon going through the slits, or 1 electron in this case, once a minute or once a second or something like that when you only have 1 in, but still the wave function is diffracted, deterministic, goes through both slits, but you don't see the electron. The electron it interacts with the screen or your detector. That's where the entropy jump occurs. That's where the collapse occurs.
When this experiment actually happened, when the year?
This particular one with electrons, I think it was in the 60s or something.
In the 60s. I think so. So they really checked this.
Was it? Do you know when it was?
Classical wave dualism, neutron diffraction experiments.
Neutron diffraction, but we've even now seen diffraction of more complex things. But the electron, when you have a very low rate, so that you only have 1 electron at a time, was, you could do it with neutrons as well. You get the same thing. In fact, more complex things are showing diffraction too. Now we're seeing all sorts of, even. I mean, this was amazing to me that buckyballs actually have been shown to have diffraction patterns of 1 micron fringes. But a lot you see is saying, let's divide the world into microscopic and macroscopic systems, small and big. It's not, in my opinion, small and big at all. It's because I can have, it's the number of states, or the complexity, or simplicity and complexity. Because you now, you can do these experiments where you have entangled photons coming a large distance apart, right? And you know that the polarizations have to be correlated, but you don't measure them until you measure 1, and then the other one is determined, right? And they can be kilometers apart. And they would be simultaneously determined in 1 frame of reference, but in a different frame of reference. One will be first, and the other one will be second. But so I'm just saying that it's not a distinction about microscopic and macroscopic, but so it's an odd notion to think that you have a wave function of a buckyball, but these apparently these experiments are showing fringes here. So and yeah, and the word entanglement, actually, I think Schrodinger invented the word entanglement, where you have a system or state that that you have to describe as the one state as a wave function, and then if that state was two photons that can be far apart, they're entangled in the sense that they're part of the same wave function, and when one of them interacts, therefore causing the entropy to jump, that determines the other one. All right? So, and of course, you know about Bell's inequalities and so on. So, for example, pi 0 here, and it's two photons, and that can be in a large vacuum chamber, and very big. But when one interacts, if you had a polarimeter measuring the polarization of photons, for example, and the other one is determined, and that is when the wave function collapses. And of course, thinking about if you then shoot this past you at maybe relativistic speeds, then the order of the two interactions can change from one to the other. So so I think that I could talk on about some other things, but let's discuss this for a little bit, because I think that maybe it's just discussed in the literature and rejected, but I haven't seen that. People still are talking about measurements without defining what they mean by measurement, and observers without defining what they mean by observers. And to just accept or say that any jump in entropy, where usually it's a huge jump, even if it's logarithm of a number, it's a huge jump, right? When a neutron decays or something like that.
For me, it's not yet clear the connection relation between the two of your statements. One statement for me is very clear, this entropy jump, really huge, even logarithm. Another statement, wave function collapse. I still do not see sort of logical consequences that entropy jump and the consequence wave function collapse. I do not see this consequence, logic between these two. And somehow I'm missing this.
Well, do you mean do you mean that you don't understand the mechanism for wave function collapse, or you don't?
So I think the two statements are different.
Yeah, they're different statements, right?
And you are saying that one
one happens when the other happens.
Yes, one happens when the other happens. This I do not see this relation between these two. Why? Wave function collapses when you have entropy jump.
Why or how?
Both.
Both.
At least
but
why?
How? Yeah.
Can I suggest something?
Yeah.
I think you're saying the entropy increases when the event happens. And the event happens when the wave function collapses. It's a different way of saying the same thing.
Yeah. Chicken and egg, right? So. Yeah.
One means the other.
Yeah. I think. Yeah.
I think you're also saying somewhere along the line that there's no such thing as a quantum state that includes both the radioactive nucleus and the cap. There's no global quantum state that includes both of those objects at the same time.
Because the cat, the cat was an absurd. Schrodinger invented it as an absurd example, but a cat has, 10 to the 10 to the 28 atoms or 10 to the 25 atoms.
You can't make those all coherent.
So it can't be coherent. Yeah. So it's sort of to do with decay. Now, one thing that sort of puzzling me quite a bit is, and maybe Albrow can show some light on this, is about decoherence. And suppose I have my experiment, and I can send two high energy gammas, okay? And well, it's like this: E plus, E minus. Okay, gamma gamma, gamma gamma, P plus E minus. But but it could also be mu plus mu minus or q cube r. And if this is happening inside a vacuum vessel and so on, neither the electrons nor the muons interact with anything until they hit the walls of the vessel, which could be far apart. Now, but when does nature decide whether it's going to be an E plus E minus or an E plus E minus? This is a space-like exchange here. It's a T-channel exchange. But given the fixed energy of the incoming photons, the electrons and muons travel out at different speeds because they have different masses, therefore different momenta. So I think that if you look at an extremely small timescale, then you just have to have a superposition of all the states there, and then after some time, which is of order, Fermi time or something like that, then it becomes one or the other and loses coherence with the other states. Is this sort of what you might think, or?
So Cat, still a little bit of time is between dead and alive. Very short time, but still there.
Yeah.
I don't think you know, whether it's an E plus or E minus until you measure it.
Okay.
And
Measure it by measuring it in my language. That would be until one or the other interacts with something.
Well, yeah, it has to interact with.
Has to interact with something, right? But then,
But if you could find some way of, interfering with muons and electrons, you would get the same sort of, interference pattern that you had, about the slit experiment.
because I was wondering about that too. But then, if let's say, so I put in the two photons with a total center mass energy of let's say 1 GeV, and then if it was an electron pair or a muon pair, they travel out at different speeds. So imagine my detector is equally efficient for electrons and muons, but as soon as one, I can even imagine I know the time the photons came in. As soon as I measure one as an electron or a muon, it determines the other one to be an electron or a muon. So in other words,
And you can use time of flight arguments.
I'm assuming that speeds are different enough that
To distinguish the two
yeah,
different
yeah,
detectors.
yeah, yeah.
Has a differentiation. I mean, it's even worse or better in the case of neutrinos,
Okay.
which often move very relativistically and have very, very small masses.
Yeah.
They're slightly different. So the distance you have to be away for you to tell which mass eigen state it is in by the time of flight argument might be very large.
Yeah, yeah. But yeah, so
And so there's all sorts of interesting interference patterns you get
yeah.
in your detector.
So we know the neutrinos interfere in mix. Electrons and muons in principle do, but to a tiny extent because the mass is so different, right? But once you're right at the point of creation of the lepton out of the photons, then for a very small time, the energy is very uncertain. It could be a superposition of electrons and muons then.
Right.
But, and are you saying that maybe the superposition continues until they actually hit and interact with a vacuum chamber, or?
Well, this goes back to Bohr's statement that you have to take the entire, I hate to use the word measurement since you don't like the word measurement, but take the
System.
entire experiment into account. You cannot treat a piece of it at a time.
Well, I'm saying you don't have to, you can't have to take the whole experiment into account. You don't take the CDF detector or the CMS detector into account. That's unrealistic. For me, that's what you have to take into account. Only the system that
Well,
is.
but that's only because it's built so that it doesn't really matter. You could have a system which behaved in a way which is very dependent on what it measured. And then you would have to take the wave function of the entire system, the butterfly effect. Right? If a quantum mechanical fluctuation can change whether it's a hurricane in Florida, whatever, then you might want to treat the whole weather system as a wave function. But,
Well,
but that's not how the CDF detector works. That's not how most macroscopic systems work.
No, but macroscopic, I think macroscopic and microscopic are not the right words because they imply size, whereas we can have things. But whether the Higgs, we could have run the LHC, and because of a random fluctuation downward in probability, we didn't produce any Higgs bosons, right? So then, and the detector wouldn't have seen them, but I don't know where I'm going with that. It's totally not realistic. I'm saying that you don't have to take the whole detector into account. You only have to take the first point of interaction into account, the first point, wherever that was.
So if taken to come back to your picture of gamma gamma, E plus E minus or mu plus mu minus, and imagine that we do not have any detector, just these particles and then and they have plenty of space to travel.
Yeah.
Then before interaction happens, the system actually is in superposition of E plus E minus and mu plus mu minus. We cannot tell that the system is either one or another. It is vector with one and another component there. Although they do not interfere because they have different masses and so on, and we would not be able probably to distinguish by some experiment, I don't know, to see. But still, in principle, we may only tell that the system is a linear combination of these two. Maybe, I don't know, if they have years to travel. Then for years the system is there. So then the cat again, I'm coming, if put cat there, cat is still a superposition of that and the line.
Well, you're equating cat and mule. I mean, I could easily agree with you that once you do this, you have your machine, you collide gammas, and you produce E pair or mu pair. You don't know which. They travel in a vacuum for light years, and then on a distant planet, somebody says, that was an electron. Okay, the other one immediately has to become an electron. And that is consistent with my thinking about this, although I actually think that it's equally likely that I can equally go with the idea that when this happens, I've got an electron wave coming out and a muon wave coming out, but they're coming out at different speeds, so they like decohere close to the origin, and actually, if they had very similar masses, then the decoherence would be longer, and K long, K short, for example. So they've got very similar masses, so they propagate as a mixture. Let's see, the K0, K0 bar got exactly the same mass, but K long, K short got different masses, and they interfere, and so that's another, actually here's another interesting experiment about the quantum mechanics. So here you set up a phi factor, phi, E plus E minus goes to phi. And so you do it for scattering, set that up, and it can go to K short, K long, but it cannot go to K short, or K long because of CP. So it goes to K short, but and as it happens, both of these can go to pi plus pi minus, pi plus pi minus, pi plus pi minus, and because of CP violation, they can both go. But because the initial state is antisymmetric, they can't go at the same time. All right. So if you plot and let's say we're in the center of mass, phi is at rest, so they've got the same momentum. So if you plot the time of the right going decay against the time of the left going decay, you should have a hole in there, a zero in there. And so if you you fix one distance and you look at the other distance, you'll see a hole in it. And actually, I mean, that is basic one. And the hole is filled in a bit because of CP violation. So it does get filled in, and it's a way of measuring epsilon as CP value parameter. But now think about that. So now this means that when this decays over here, this one is forbidden from decaying at the same time, but that's a frame-dependent statement, isn't it? If I boost the whole thing, then what is simultaneous in the best frame of this is no longer simultaneous. And but so what's coming out is K0, K0 bar, but each of them is a mixture of K short and K long. And when one decays, the other one immediately becomes the other, right, to keep the symmetry of the system. So I don't know how wave functions collapse. I mean, I don't know that, but I think, you know, there's a reluctance to accept the reality of it. I think it's a real thing, and the wave functions are real, and they do collapse, and it's you shouldn't say it's instantaneously, but it's space-like. So the collapse, the wave function over here going from a certain value to zero, when the interaction takes place over there, is a space-like exchange, but there's no energy or momentum being exchanged. So in that case, I don't think it's inconsistent with special relativity. But I mean, you know, okay, it's a philosophy meeting, not a physics meeting. But if we really understood, you know, how wave functions collapse, I mean, then we would. I'm not going there. I don't know that. I'm just really, I think, basic messages. Expunge the words observer, measurement, consciousness, and replace them with entropy jump.
Roger Penrose making strong statement that collapse of wave function is inconsistent with deterministic equation of quantum mechanics or quantum field theory. That contradicts. That's his statement of Roger Penrose.
Oh,
yes, I do not understand why it is inconsistent, but I heard it from his lectures repeatedly. He's saying
I thought he said
inconsistent.
I heard him say once that wave functions collapse had to do with gradients in the gravity field or something.
Yes. He somehow related to gravity. This I do not understand either.
That when the gradients, you can only go so
It's hard
far.
to imagine that gravity has for me has something to do at that scale. But anyhow, he is insisting on it.
Yeah. Is it?
I think, you know, since this philosophy is not a science view, but from a scientific point of view, you say, well, is there something that you could measure that could distinguish that quantum mechanics doesn't predict, or something like that? And because, like, you know, as my quantum mechanics teacher taught me, said in graduate school, we all young people were busy worrying about these issues, was that quantum mechanics tells you how things are correlated, and that's all you could ever measure. So don't worry about what's under the hood, because
my sin is looking under the hood at what's there, you know. Because the experiment, there was this the experiment that measured Bell's inequalities, right, Aspen and so on, and showed that quantum mechanics is obeyed by the experiment, and experiments that were classical could not be true. But I'm not arguing with that. But I think my understanding is that this experiment.
Because you're making statements like the other thing immediately became a muon or something.
Yeah.
Which is adding all sorts of structure to reality, which has nothing to do with what you could in principle measure.
attracted to.
I mean, because what you can measure is, well, you can say, well, if this guy measures an electron, then that guy's going to measure a positron. So when they compare
Yeah,
notes,
yeah.
they'll always agree with each other.
Right,
That's
right.
the only thing you can talk about.
Right, right, right.
And,
The other thing,
and, you know, and then you can have the many worlds interpretation where, well, we're just all in the same part of the wave function, but, you know, there are other parts, and they're equally, you know, valid. It's just that it's not part of our universe. I mean, there's different ways of going.
yeah.
But the question is,
I mean,
can you distinguish them? No.
Not scientifically,
Can't
right?
distinguish.
It is metaphysical question. Question
Yeah.
about interpretation of quantum
Yeah.
mechanics, not about theory. Theory is complete as soon as you are able to predict measurements. That's it. That's nothing to do with theory. But we are still not quite satisfied because we see this paradox and we don't understand why. Does consciousness do something about this? Or what happens with true reality? So we are still trying to make bigger picture outside of
let's be
theory.
in a big-
Cosmology, you know, especially early universe cosmology, a lot of these issues become more atrocious, you know. Like, you have a system where, I mean, take inflation, like, you have this idea that you have this scalar field which monotonically rolls down the hill and goes in a certain direction. And then, like, you say, well, actually, what do we measure? Well, we measure the universe as big and filled with normal matter today. And then maybe we measure, you know, gravity waves and density fluctuations that happen at the beginning of inflation. So we measure things at 2 points, you know, and so you could ask the question, well, how do we, you know, so in principle, there's a whole bunch of paths that could connect the 2 points. And you could ask the question, did the scalar field roll down the hill? And then people say, well, you know, how can we know? Let's quantify what we measure today as the universe is very large. So we want to weight things by volume. And if you do that, you find out, well, actually, the scalar field is much more like, to produce more volume, it's much more likely to roll uphill than downhill. And so, because there's all sorts of paths that connect the two measurement events. And,
Yeah. So I think, you know, everything I said, it doesn't change any predictions about measurements or
well,
not.
I think in cosmology it does, because you can. Well, because you have a hard time quantifying, because there's all these because the space of final states is very large.
Yeah.
You can't really put a measure on it. And so people say all sorts of different crazy things.
So
I mean, in an experiment, the possible final states is finite. You can put a measure on it. You measure an electron or a positron.
the suggestion of Everett that some people seem to take pretty seriously, that whenever a quantum event occurs, the whole universe collapses or becomes splits in two or something like that. It seems totally, I mean, you know, things, it's mad. It's just mad.
It is absurd,
It's
the
absurd.
strict definition of absurd.
But,
Yeah.
but I think it basically, it goes against our understanding of the way the world works.
Understanding of what they
The way the world works.
Yeah.
The world works as a sequence of definite events. That's the way the world works. And there's a fixed reality, you know. So that's our conception of the world. And certainly that particular picture doesn't obey it. But maybe that doesn't mean it's not true. And how much are we biased by?
Scientifically, I think it cannot be refuted on the pure scientific ground. But I think people who refute it, they refute it on the ground of absurdity. They do not accept absurd world. This is purely metaphysical, not scientific. It is metaphysical refutation.
Yeah,
I
but
do not want to accept absurd picture.
Yeah.
That's it. It is fundamental
Why is it
principle.
absurd?
Because it doesn't
Because
have any meaning or reason behind of it, any sense.
We're talking about Everett's many worlds
it's
thing.
too-
Many
I mean,
worlds,
again,
Everett, yeah, I'm
it's-
talking about it.
It's absurd because it doesn't correspond to our understanding of the way the world works, and secondly, because it has no observational consequences.
Yeah.
It contradicts to any definition of meaning or sense.
That's quite distinct from the multiverse. That's a totally different thing, right? The multiverse is not
Well-
nothing to do with Everett stuff.
Well,
Everett's
some-
saying
well,
the whole
some-
universe splits.
Well, sometimes people include multiverse to, that's one of,
It's one of the multiverse pictures.
One of the
one of the
multiverses.
types of big ways that you can have a multiverse.
Multiverse could
But
be.
it's not the original, or, the multiverse idea was separate from that.
Yeah.
But then I think Tagmar.
Tagmar has
That's a
four
list of-
layers of
list
multiverse.
four multiverse, that's what, you know.
4 layers, yeah.
Yeah, so, but anyways, it's not the cosmology one.
No, it's a specific layer, it's a separate layer of
It's the
quantum
Albrow layer.
mechanical.
I was hesitating because I had a different sort of presentation about cosmology actually, but I mean,
Yes, it's
is it okay? I mean, people.
much more
sure.
like it, so
Okay.
I would
I'll
be
try
happy
and
to
keep
hear,
it
so
down.
I think we all enjoyed your
minutes.
talk, Mike.
Thank you.
Wonderful. So please send me your file, huh? So
Okay,
I will
yeah,
put
yeah.
it now.
So you have to go with me, but I appreciate attentive ears for this idea of cosmology because
Ah, sure.
So
We are eager to
it's
hear.
again more philosophy than physics. I tried it out with Paul Steinhardt actually, and it also.
I read actually your papers, this one,
read that
and,
paper, okay.
and trying to prepare myself. But the question was, and still is, the relation between these two. So
Yeah.
entropy jump,
Right.
understandable, clear, and wave function collapse, still mystery.
Yeah, right. So
What's
this,
the relation?
I don't think this idea is actually contradicting inflation, except to say that I don't think there could be a singularity in an origin. I have, so let's take two hypotheses and see where they lead. Hypothesis one is no infinities in physics. Okay. No infinities. Infinities in maths, fine. Infinities, no, okay. Big numbers, 10 to the 100, okay, but not infinity. Which implies no infinitesimal, no singularity. Number two is no boundaries. So no boundaries to space-time.
So apeiron of an oximander. So you're following an oximander apeiron. No boundaries. Apeiron hypothesis.
Yeah. So Einstein said, well, maybe the universe is closed free space and there's no boundaries, but it's finite. But what I'm proposing is that time is also no boundaries, but finite. So how could these things be consistent with each other? And one solution, maybe it's a unique solution, I don't know, but is to have a sort of picture of the universe somehow like this. So this is the Big Bang here. And we're now in an expanding universe here. And these are baryon world lines coming up. And the universe is expanding. But because I don't have infinite future time, the universe has to recollapse. So this is now Big Crunch. And time coordinate is like this. Space coordinate is orthogonal to it. So space, time, and I've now got time as a closed loop, like all three spatial dimensions are closed loops. Closed. Right.
You don't need a singular Big Bang.
I don't want singular,
That dense,
or very small.
Very dense.
Very dense, very small. Now, about density, though, I think this is now, so it's a toroidal sort of structure, but you're pinching it down here. So I call it, I don't know what there probably is an official mathematical or topological way of saying it. I call it S3T1, 3 space and 1 time dimensions. Now, then, because this is closed space-time, it has to have total energy, mass energy 0. It can't have gravitational lines of force coming out because there's no outside, it's all inside. So the total energy of the universe has to be 0, so we have negative potential energy that exactly counterbalances the mass energy. And then when you have the Big Bang, Big Crunch, now I'd like to zoom in on this thing. As I said, no infinitesimals, but that's our universe. Keep putting it like that. And down here, these are baryon world lines coming out here, and they're coming back in here. Okay. So if you now look at this, it's rather like a baryon-anti-baryon pair creation, or universe-anti-universe pair creation. If you just look at it from this point of view, means that the question of what happened to the antimatter is changed. The universe we're in, the connected part, is all baryons, essentially. And all the antibaryons are here they are identified with far future. So Big Bang time, and I don't mean things happen again and again as time goes round and round. It's just, that's it. That's the whole of space-time. It's like that.
And then, what happens after that?
But there's a boundary.
Collapsed.
I mean, there's no boundaries, so it's,
No boundaries.
so it's periodic, or
Periodic?
the wave functions have to match at all time slices, including the one near the Big Bang. You know,
The wave functions have to match there. Yeah, I mean, it's,
they match there, and they match just the way they match between now and 10 minutes from now.
So it should be periodical then, right?
Well, it's
I don't have any periodicity any more than the surface of the Earth. You go round the Earth, right? You go round the Earth, and that's, you know, 40,000 kilometers. It don't go round and round and round. It's just, that is it. That's the whole of the surface of the Earth.
So
This is the whole of space here.
and I think that's what most people mean by periodic. It's
Okay.
exactly periodic.
Oh, maybe, exactly. Okay.
Yeah.
or it is spontaneous, just like decay of atom, state, metastable state, like metastable bumps, big bang, big crunch, and again metastable state. You can think
Well,
like that.
as I see it, I mean, this is like, it's like analogous to an electron-positron loop in a vacuum. Okay, it's like a virtual loop. And seen from outside, if you dare to talk about outside, this is space-time in here that we have access to. That's our closed space-time. But maybe it's embedded in some outer big space, big time, that is, and in that outer big space, big time, where I've got T here and space here, which could be 1 and 2 dimensional, there are, you know, your 10 to the 100 universes as like vacuum fluctuations in this outer space time, coming into existence and out, but they don't talk to each other because they're all closed space times, so they don't interact with each other. So this outer space time doesn't have to be expanding or contracting because there's no gravitational interaction between these universes. So this could be, it could be like a steady state universe, a steady state. This is a Big Bang and this is a steady state. And it's in outer space time, so inner space
So
time.
it is bigger space where these big bangs and big crunches happen.
If you like.
They don't interact with each other.
Yeah.
Sort of ideal guess of universes.
Fluctuating in and out of it fluctuating, and because each universe has got total energy 0, obviously total charge and Barnum is 0 and everything like that, it's a totally neutral thing. But you can imagine that in this outer space time where these 10 to the 100 or whatever universes are popping into and out of existence, there's no physical connection between them. Therefore, you know, the laws of physics can be different in them, or at least the parameters can be. So, you know, some last in our, some don't last any time to produce stars, and some expand too fast, and so on. So, and here the anthropic principle comes in if there's 10 to the 100 of those. But then, you know, a large number can be good for life just by random. But I don't use the word infinite here. So that's, you know, like Steinhardt has got these oscillating universes where he has these brains that collide and so on. And he keeps doing that and doing that and doing that. And each universe is created afresh. And I said, well, why don't you just identify, you know, in some senses like bounce. Why don't you identify that point with that point, and then it's just one thing and that's it. Space.
It's a matter of definition, actually, right?
Is it?
You may consider them just different universes, if they do not. If there is no causal relation between these two.
But here, you know, with this I have one problem, which was about entropy. Exactly, going back to entropy, because you know we know entropy is increasing in our universes. Neutrons decay, but they don't go back, right? So how come the entropy is increasing all the way here? And when Stephen Hawking had talked about, you know, time reversing at the biggest power, entropy increases all the way here, but when you get down towards the big crunch, it decreases, because now electrons, neutrinos, and protons can combine to form neutrons, and gamma and electron combines to form an E. So all those processes.
But why, you know?
Should be forgotten.
But why is it like a big mess of black holes rather than?
Yes.
Yeah.
I mean, normally, if you would do this without requiring the periodicity, what you would end up with when you very different than
Yes,
when you started out.
entropy will be much higher.
But if you just sort of mathematically say, well, we assume a periodic, exactly periodic situation.
But how is it possible
And we
with all?
And we require the wave function to be exactly periodic.
How is it possible?
Then you would basically exclude all of those possibilities by the boundary conditions.
Yeah.
But with those
Yeah, I made that
entropy
out.
jumps
I
which you
think that's
mentioned,
sort of
how
the
is it possible?
talking.
They go back. I mean, all the things I talked about go backwards as a big crouch. But okay, it's interesting what you're saying is that by imposing boundary conditions, I mean, well, by boundary conditions we mean periodic conditions, right?
Well, there's periodic, yeah. So periodic is different than oscillating. Oscillating.
Yeah. Okay. So you're requiring the physical state there and there are
The same.
the same. So what happens here? I mean, black holes. So, okay, black holes. So as the universe gets colder and colder, then black holes of bigger mass will start evaporating and so on. Hawking's right about that. But a rock or the Earth will not become a black hole, or will never become a black hole. But eventually, the protons may decay, and the Earth may decay because protons are decaying after 10 to the 38 years or something like that. But then, so you might have in this far future an extremely dilute universe. The protons have decayed, electrons have not decayed. There's electrons, protons, and neutrinos. And just that, and 1 per cubic light year or something like that, decreasing. And then it's got to come back together again. And black holes will all have evaporated, if Hawking's right about that. But I wonder, yeah.
Well, I think that you have problems with, I mean, we fortunately, unfortunately, live in a universe where the entropy doesn't change very much.
Yeah.
Right? Almost all the entropy is in the microwave background, the cosmic neutrino background. And everything else is sort of small compared to that.
So the reactions going on in the stars and sun do not make much more entropy. I mean, they make a lot of photons, right? But not.
Well, they don't make that many more photons. They don't make as many photons as the cosmic microwave background. It's only a few orders of magnitude difference.
Okay.
But the baryon to photon ratio, but because you have a little bit of star formation, the entropy per baryon is actually increasing. And how can you have? I mean, if the baryons are stable,
Yeah.
the baryon number is a conserved quantity.
Yeah.
Then how can you have this periodic thing? Because we're increasing the entropy per baryon by stars, as you say.
Well, yeah, but what I'm supposing at this big crunch, if we look at the time when the universe has come down to the size of your grapefruit, as it were, then the photons are all absorbed on protons, right? And they're all absorbed, so you end up with the baryons are conserved. Let's suppose.
That you're supposing that.
I'm supposing
It doesn't
that.
have to be true.
It may not be true, but you can, I think, suppose that. And then actually about baryon conservation, that brings black holes.
If you have any conserved quantity, then I think you have problems with the entropy having increase per conserved quantity. And
But
maybe
entropy is not conserved. Entropy can go down as well as up, except it's extremely unlikely to go down.
Well, no,
in
but I
a
mean,
standard
in
universe.
the collapsing universe, it's not going to go. The entropy is not going to change. It's not going to go down.
Why not?
When you compress a gas, the entropy doesn't go down.
No,
It goes
but
up. I mean,
we're now.
if it doesn't go up much, you call it adiabatic. But it doesn't ever go down except for.
Well, if I have got the 10 to the 80 nucleons in the universe and I've crunched them down, then all the photons are going to get absorbed in there. I think.
No, the photons aren't absorbed.
Why not? There's not room for them.
No, they just get hotter, and you produce all sorts of other particles. Thermal, a sea of free quarks. And in standard model, almost all the particles are quarks. So the quarks will have all the entropy.
Yeah. So,
But
actually,
the entropy won't go down.
Unless you have an option to have a single particle of all of them, sort of.
well, you know, I
Super
ask a question.
boson.
Say there's about 10 to
Simple.
the 80 nucleons in a visible universe, in this closed universe here. How without having a singularity at the Big Bang or the Big Crunch, how small could it be? And if you just take
you know, the number density goes like T cubed. So if you have so many particles,
But then
you just pick the temperature where they fit in the volume you've got.
But I'm choosing the volume that could fit in 10 to the 80 particles if they're all conserved, they're all 10 to the 80 protons in there. But give each one a Planck volume.
Well, the thing is there's something special about Planck.
Yeah.
That's a good question. Maybe there is. Maybe physics is different.
And entropy could still go down. So if entropy really can go down, then it would be a solution.
Because I was
Does your model go up to the Planck?
I
Because there's all these singularity theorems which say that you have to produce a singularity, right? If GR is true and the certain equation of state is satisfied, then there's.
So let's say, it's GR that says that you have to have a singularity at the beginning of Big Bang. Singularity.
There's singularity theorems which say that if you have certain final, suppose we have a certain condition of the universe today,
Yeah.
and the equation of state of matter obeys certain sensible rules, which it turns out probably aren't true, but we used to think they were true. Then there has to be a singularity in the past. If you obey Einstein's equation.
But the singularity is a zero size, not Planck size, but zero size, right? I mean, when you get down to sizes of Planck size, then we don't know the physics there, right? So.
Well, no, I'm just saying you could imagine that your periodic universe doesn't get so small that you have to go up to Planck temperatures.
Okay.
You could avoid the Planck issue entirely.
Yeah.
But you need some other sort of either weird equation of state or other gravity theory to avoid giving the singularity theorem. You know, people don't probably think there isn't really a singularity, but it just shows you have to have the physics have to change before you get there.
Yeah.
And so there's some interesting physics in the past that actually happened.
I saw a quote from Stephen Hawking, actually, who said that we don't actually really know that there's a singularity at the center of a black hole, but we're not sure about it. We're all sure about it, but because it depends on physics as you get to that extreme conditions there.
Right.
But what you say is interesting, that maybe this is a legitimate sort of topology of cosmos, but imposing periodic boundary conditions at the Big Crunch and Big Bang would be constraining, more constraining.
Yeah.
That's very interesting.
And it might actually lead you to a Hawking-like model where the effective arrow of time changes.
Yeah, it was Einstein. He talked about that changing at when the universe was at its maximum extent.
Right. Einstein.
I started thinking about. I was Paul Davis. Paul Davis. He he's right. So he published in Nature. This was in '72. I know that where he talked about bouncing universes like that. Okay, and we're in here. Okay, and he said, well, suppose the arrow of time reverses in alternate universes. It seemed to be a really strange sort of thing to think about. So I said, that's going to happen. This really is. I should take this part here, call it A, and put it over here, and then the arrow of time is going back. Is going that way, and then I've got I don't need any more of these. So I've now got this universe and universe pair creation. And I wrote a little letter from Nature pointing this out, and they published it actually. But it's very, just a short thing. But now I'm saying, well, I don't need two. I can just have one like that. And I said this is reminiscent of vacuum fluctuations, like electron-positron pair And it does, I think it implies that omega should be